Welcome to Atoms to X-rays, the series that brings you the wondrous variety of research in physics, chemistry, and mathematics here at the University of California at San Diego. This series has been developed so we can share the excitement of exploration and discovery, and the promise which that discovery holds for our future. I'm Mark Thiemens, Dean of UCSD's Division of Physical Sciences, and I'm proud to dedicate this series to the memory of my friend and colleague, Professor Kent Wilson. Through his innovative approaches to learning and teaching, Kent opened new windows of understanding for all of science, as well as for generations of students. We hope we can open some windows to the world of the physical sciences for you too, as you enjoy this edition of Atoms to X-rays.
What I want to talk about today is the mystery of and the importance of empty space, the vacuum, the void, nothingness. Of course, philosophers have discussed and thought about nothingness for millennia. What's kind of surprising is that modern physics has a lot to say about this subject, and in fact, what's also surprising is how important this subject has become. This is a picture of the Keck Observatory on top of an extinct volcano, Mauna Kea, in Hawaii. In this observatory, astronomers are measuring the tiny flashes of light from distant supernovas billions of light years away. And what they're trying to do is understand the vacuum, what happens in the vacuum here. Here's a picture of the CERN particle accelerator near Geneva, Switzerland. That's a 15-mile-long underground tunnel there. And what the particle experimentalists are trying to do here is to create tiny ripples in space-time called Higgs bosons. And the purpose is the same, to understand what's happening in empty space. So both those group of scientists have similar goals. They are testing predictions of some absolutely bizarre theories of what happens in the vacuum. Okay? Superstring theory, particle physics, cosmology, astrophysics, these may seem like separate subjects, but in fact the current theories have forced those theories together, and if you want to understand these things, you have to work on both the smallest scales, like we hear the particle accelerator experimentalists do, and the largest scales. So that's what I want to talk about today, and let me start by talking about particle physics on the smallest possible scales. One way of looking at what the goal of particle physics is to understand what the most fundamental building blocks of nature are. That's what they kind of do. And over the years, the method has stayed the same. What you do is you take something and you smash it as hard as you can, and you see what it's made out of, okay? So starting here, you start with like a block of ice, and you smash it, and what you're going to get is water molecules, okay? No matter how hard you hit that with a sledgehammer, you're just going to get water. So you say, okay, ice is made of water. But in fact, if you then take those water molecules and you take some other instrument and smash them even harder, you'll find that they break up into hydrogen and oxygen atoms. And so you say, okay, that's the most fundamental thing, atoms. And this has been very successful for hundreds of years, in fact. And in fact, all of the elements, everything we see in the world, are made of the 92 elements of the periodic table. So in one sense, we could stop here and say, okay, we're done, right? Everything is made of atoms, okay? But that's not really true. Because if you go back to the atoms and you smash them even harder with a more powerful smasher, okay, they break up into protons, neutrons, and electrons. And in fact, we now know that everything in this room is actually made of protons, neutrons, and electrons. That seems like a very simple place. So maybe we should stop there. It'd be nice to stop there, but unfortunately, or fortunately, if you take your protons or your neutrons, these are neutrons, and you smash them together even harder, and you need more and more powerful smashers to do that. That particle accelerator I showed you in the slide is the world's most powerful smasher. Okay? What you find is that the protons and neutrons are made of quarks, up and down quarks. Okay? So this goes on, and that's how far we've got. So the question is, can you understand the most basic building blocks? And I'm not going to review all of particle physics, but to suffice it to say that after decades now of smashing and theorizing and synthesizing, we are now in the position of having the standard model of particle physics. In other words, we have figured out what the most basic elements of matter are, given the level of smashing that we can do. And this is it. It's a very successful theory. It consists of some fundamental particles, quarks, up and down quarks, and leptons, like electrons and neutrinos. They come in a mysterious triplicate of 3 generations. No one knows why exactly, though we'll get to that at the end. It's a quantum field theory, okay? And the quantum field theory has symmetries in it that tell how to combine these together to make protons and neutrons and everything else we know. Those same symmetries associate with different force particles. The photon is the force of electromagnetic. We have strong forces. Those same symmetries say how these things interact and build everything else out. It's a very complicated theory. It has lots of math. But with this theory, you can make thousands of predictions, and thousands of experiments have been done testing it. And in every case, the theory agrees with experiment. So whether you like it or not, this standard model of particle physics is the best description we have of nature, and it works. Okay? So we are forced to kind of use this model by experiment. That's how science works. Now, you could ask, if the theory works so well, why are we still working so hard, excitingly, to build these particle accelerators and test this theory? I said it worked. In fact, it's because there's a troublesome part of this theory, and it has to do with this big Higgs, H, over here. Okay? When people first worked out the symmetries in this theory and how to use those symmetries to predict how things go together, there was a troublesome point. And the troublesome point was that those same symmetries imply that every fundamental particle is massless, has no mass. Okay? Now, massless particles can exist. Particles of light, photons coming out of the light bulb there, are massless. And of course, particles of light move at the speed of light. In fact, what is the case is that any particle that's massless has to move at the speed of light. Okay? Electrons have a mass. The atoms in my hands have mass. And the reason I can move my hand at a foot per second like that is because I have mass. If I didn't, my hand would have to move at the speed of light. Okay? So the fundamental symmetries that make this theory work say that every particle is massless. Sounds like something terribly wrong with this theory. So what to do about that? Well, in 1964, this guy, Peter Higgs, and some of his friends came up with an idea. A very possible but very weird solution. He said, it's called the Higgs mechanism. Okay, let's suppose the particles are massless, fundamentally massless, no mass. Okay? But take the universe and fill it, completely fill it with a quantum field, a smooth field that acts to slow down the particles. Okay? So it's kind of like imagining this room full with water, and I move my hand, and I have to move it through water, and that slows my hand down. Okay? So this is the idea of the Higgs mechanism. The universe is filled with this all-pervading, omnipresent field, okay, called the Higgs field. If it wasn't for this field, things would move at the speed of light. In fact, intrinsically, the electrons in my hand want to go at the speed of light, but they can't because they keep interacting with this Higgs field. Okay? So pretty weird, pretty weird. What makes the difference? Why are some things heavier than others? Well, in this theory, everything is massless, pretty much, except that heavy things interact more strongly. Like moving a pencil through water is easy. Moving a ping pong paddle is hard. Right? So how heavy something is in this theory is just how strongly it interacts with this omnipresent Higgs field. Okay? Now, can you feel this Higgs field? I mean, this is what the standard model says. This room is filled with it. Can you feel it? Well, in a sense, you can feel it because otherwise your hands would be moving fast. The weight that you feel is, in fact, interaction with the Higgs field. So we are swimming in this invisible field. Now, there are other invisible fields here, right? Like the Earth's magnetic field is right here in this room. You can't really feel it, but if you have a compass, it would line up and you could do it. The radio transmitters around San Diego are filling this room with electromagnetic waves. You can't feel them, right? They're going right through your body. But you take a radio in here, and it'll move the electrons, and you can pick up, you can feel those fields. Okay? Now, and even the light coming out of this light bulb is, in fact, electromagnetic radiation, ripples in that electromagnetic field. But there's a big difference between these fields and the Higgs fields. If I turn off the lights, if I turn off the radio transmitters, if I stop the dynamo action in the Earth's center, then, in fact, the electromagnetic fields will die away, and we'll have no electromagnetic field here. The Higgs field is different. The Higgs field is there even without sources. You can't turn it off. If you could turn it off, everything would start moving at the speed of light. Okay? So you can't turn it off. So we say it's there even with no source. It's a vacuum field. It's there in absolutely empty space. Okay? So empty space, what we mean by empty space is when you take out everything else, take out all the particles and all the fields that you can remove. The Higgs field can't be removed. It's a vacuum field. Okay? So electromagnetic field is zero in the vacuum, but the Higgs field is not. This is weird, but it's true according to the standard model. Now what if you could fiddle with this Higgs field? Let's suppose you could turn it off. What would happen? Well, the electrons in your body would suddenly start to move at the speed of light. The protons would just change beyond description. They'd come unglued, perhaps. They would just discombobulate. So what a weapon you would have if you could control the Higgs field. If you could point at something and turn the Higgs field off in that region, that thing would just discombobulate completely. Okay? Even better, suppose you could turn down the Higgs field like a dimmer switch on a light bulb. Okay? Well, what would happen? Things would get less massive. Right? So hey, what a way to lose weight without dieting. Right? Just turn down the Higgs field. But of course it's much more serious than that, because the mass of the electrons determine the properties of the atoms and molecules. So if you changed the Higgs field even a little bit, all the molecules would change completely. Chemistry would be completely different. Materials would be completely different. If you want to see really new materials, different than you can make out of the 92 elements that are known, you change the Higgs field. Okay? So this would be an amazing thing if you could do it. But can you do it? Well, no one's thought of any way of doing it. Okay? May be impossible. We don't know how. But we do know something, that just after the Big Bang, the Higgs field actually was turned off. It wasn't turned on. And in those days, those picoseconds, the universe was a very different place. There were no protons and neutrons. They couldn't hold together. It was just quarks and leptons in a soup. Every particle was moving at the speed of light. You couldn't build any structures. You couldn't build anything in those days. And then about a picosecond after the Big Bang, the Higgs field turned on. And when the Higgs field turned on, this comes out of the math. You can figure this out. Things could start to go slower now. Things suddenly became massive. And then you could start to build protons and later atoms and all the structure of the universe. Okay? So this weird Higgs field is an essential part of the standard model of particle physics. But is it true? Is it really there? Is this room filled with it? Well, we don't know the answer. Why don't we know the answer? Because we haven't discovered it yet. That is what those guys, those particle guys in this accelerator are trying to do. They want to see whether or not the Higgs field really exists or not. This is why there's so much excitement. See, there's a 15-mile long tunnel here. They accelerate electrons in one way and positrons the other way, and they smash them together at these stations here. And they are trying to form a ripple in the Higgs field, because the standard model says if the Higgs field exists, then you can form a ripple of it in it. Just like if you have water, you can form a water ripple. Okay? Faraday and Maxwell showed that you could make a ripple in the electromagnetic field, and that actually is called a radio wave or a light wave. And in fact, since it's a quantum field, the ripples are quantized and we call them photons, and that's what's filling this room, photons. The same thing happens with the Higgs field. You make a ripple in it, and that's called a Higgs boson. So the search here is for the Higgs boson. That's what they want to do. Okay? So for the last decade then, people have, finding the Higgs boson has been the absolute obsession of particle experimentalists. They've tried for 10 years, and they haven't found it here. Now they don't know, it's a quantum field theory. The size of the quantum isn't known for the Higgs field. So they started making little ones and didn't find them. So by now we know that if Higgs bosons exist, they have to have a mass 100 times that of the proton. Okay? That's the limit of this accelerator. It can't really reach it. So Higgs particles, bosons, ripples are very difficult to make and to detect for a couple of reasons. First, it takes a lot of energy to do it, and you need a big smasher like that. Okay? Second, it's hard to get the energy into the ripple of the Higgs field. It's much more likely to ripple the quark fields and make quark particles. Okay? Third, when you finally do create a Higgs boson, a Higgs ripple, it almost immediately decays into normal stuff like bottom quarks. So then you have the debris and you have to reconstruct, was there a Higgs boson created or not? So that's why it's taken so long. Okay? And it also takes a lot of events to do it. So the story happens 10 years in, world's most powerful accelerator had been cranked to its max and hadn't found any Higgs bosons. Okay? So they decided, okay, what we've got to do is take out this electron-positron collider, use the same tunnel and put protons and antiprotons in, which will give us a 20 times more powerful smasher. 20 times more easier to create Higgs bosons. So they decided to do this, and they were going to schedule to shut down last September. Okay? In July, something happened. This experiment here, the Aleph collaborator, this is what happens, by the way. They smash those things together. This is the two pieces of the Aleph detector. The electrons come one way and the positrons come the other way. And these things go together. There's people to show you how big this thing is. Okay? All the debris comes out into these things, and then they try to reconstruct what happened and say, was a Higgs boson, was it a ripple in the Higgs field or not that was created? Okay? So these guys at Aleph announced to the world that they had 3 or 4 possible Higgs candidates. Well, this caused amazing excitement. 10 years people have been looking. Now we've got it. Now, they were scheduled to shut down in September. So the management said, okay, run for another month. Okay? So they ran for another month. Actually, I wanted to show you. Here's what they saw. One of the things they saw. This is a picture of that same detector, in and out of the board as a smashing, and this is the debris and the different colors of the jets that came out of it. And this is very likely to have been the debris. By carefully analyzing the energy and momentum, it's very likely to be the debris from a Higgs boson. There are other possibilities, though, unfortunately. And so you have to have lots of these. They're unlikely. So you have to have lots of these to prove that you have a Higgs boson. Okay? So they let them run another month. And then they found some more. And in fact, Jim Branson, a professor here at UCSD, he's running one of the other, not running, but working on one of the other detectors. They also found some possible Higgs candidates. So it's looking very tantalizing. So they say, okay, run another month. Now, they've cranked this thing to the max because its lifetime is about up, right? They're running it way past the red line. Okay? This thing's about ready to pop. They have contractors paid for standing outside the tunnel saying, we've got to dig this thing out and put in the new one. It's costing hundreds of thousands of dollars a day to delay, And so they run for another month. And again, they're finding this signal for the Higgs, but it's not sure. So they make the decision. They say, you know what? Let's go ahead with our plan. Let's put in the more powerful machine. That will prove it for sure. Okay? So they shut the thing down in December. Okay? Happened last year. Big disappointment to people like myself. Would love to know. But because, the reason there's a disappointment, it's going to take 5 years for the new machine to be ready to run, okay, and giving data. So we're sitting here with nothing to do for 5 years, right? Except it does actually give a chance to some US people at Fermilab. They have built at Fermilab, a proton-antiproton collider. It's only about 3-4 miles around. It's not as powerful as the new one's going to be, but it started this month. So, hey, maybe the US can take back the lead in particle physics and find something. The problem, of course, is that this is not as powerful a machine. It's going to take them 3 or 4 years to get enough data to maybe see those same Higgses. So again, we are basically in suspended animation for the next 4 years or so when it comes to the Higgs boson. That's too bad. But most people actually, let's go on though and say, what can we do in the interim times before we really know for sure? Most people are pretty confident in the standard model. It's never been wrong. Okay? So we're pretty sure that this Higgs field is filling all of space, and it does exist. So we're pretty sure, and we've had some little clue there. So let's suppose it's right. Let's suppose the Higgs boson is discovered, and we know that there is this omnipresent Higgs field. There's a very serious problem with this idea, okay? Because it's been known for 50 years that if you have this vacuum energy, that's what the Higgs boson is. It fills empty space and it has energy, okay? It has a very weird effect on the universe, okay? Einstein's theory of general relativity shows that the universe has to either contract or expand, and it's been measured that the universe is expanding, okay? If you take, and it's the cause of the expansion is the matter in it. If you take the universe and fill it with stars and galaxies and atoms and material, dark matter, anything, it will expand, and the gravity of those things in it will cause the expansion to slow down. Okay? And by measuring the speed at which it's slowing down, you can actually measure how much stuff is in the universe. People have been trying to do this for 50 years. Okay? If there's enough material, in fact, the universe will eventually stop expanding and start to contract and go back to a big crunch. So this theory, this Big Bang theory, based on Einstein's theory of general relativity, is really well accepted and well tested. It explains many things. It explains the cosmic microwave background. It explains the number of helium atoms in the universe. It gives a very promising theory of structure formation and galaxy formation, explains the expansion of the universe. It's basically the only game in town. So we're really, in the same way with the standard model of particle physics, we're stuck with this model, standard cosmology. But it's been known for a long time that vacuum energy has a very different effect on the expansion of the universe. If you take a box, or not a box, but a region of the universe, and it's full of atoms, say, and expands, the number of atoms will stay the same. And so the expansion rate will go down. The expansion rate is driven by the amount of material inside a region. Okay? Now if you take that same region and fill it with vacuum, which of course it automatically is, and now you expand, you've got more vacuum. If every cubic centimeter has vacuum energy, you've got more energy. The expansion rate will go even more. Now it really takes solving the theory of general relativity and a lot of math to show this, but it's an absolutely inescapable conclusion of general relativity that if you have vacuum energy, the universe will undergo a runaway, accelerating, exponential expansion. Okay? Now, the standard model says, in fact, that the Higgs field, it fills up the universe. And it even tells how much it is. The Higgs field in 1 cubic centimeter is more than 1 trillion tons. That's how much it is. 1 trillion tons per cc. Okay? Can you feel that? Well, as I said, you actually do feel it because your hand is able to move slowly. It's what gives you the mass. But if you plug that number into Einstein's equations, you'll find in less than a nanosecond, the universe should have expanded to 1 billion times its current size. Something is terribly, terribly, terribly wrong with this theory. Okay? Where's the problem? Okay? Well, in fact, there's a very easy but very ugly theoretical solution to this. Okay? And it's one of the major unsolved problems in particle physics. Here's the solution. Okay, the Higgs field fills all of space with more than 1 trillion tons per cc. Let's take another field, an unknown ad hoc field that's never been invented, just for this purpose we'll invent it, and it fills all of space but contributes minus trillions of tons per cc and cancels it out. Now, in regular life, we can't have negative energy. Everything we have is positive energy. But in quantum field theory, the vacuum is allowed, perfectly consistent mathematically, is allowed to have negative energy. So there's nothing mathematically or theoretically wrong with having this minus vacuum energy. Except it's very weird that we have to take some ad hoc field and cancel out this stuff. And it's even worse than this because lots of other fields in particle physics, the quark fields for example, also contribute vacuum energy. And that has to be canceled out too. Okay? So this is called the cosmological constant problem because the vacuum energy, cosmological constant is another name for the vacuum energy. The cosmological constant was introduced by Einstein. He later called it his latest blunder, his biggest blunder. It actually is here now, and we'll see why in just a second. So what's interesting is that this cancellation has to happen, and no one knows how it happens. In fact, some of the biggest names in particle theory, Ed Witten, Stephen Weinberg, have said that the most important unsolved problem in particle physics is the cosmological constant problem. How to arrange this cancellation. Okay. Now, there was a huge new wrinkle to this, happened a couple years ago, by people playing around with telescopes like this. Some of my friends at Berkeley went out and said, well, let's see, let's test this hypothesis. Let's see whether the universe is expanding. How is it expanding? Is it speeding up or slowing down? Is the universe filled with ordinary material, in which case the expansion should be slowing down, or is it filled with vacuum energy, in which case it should be speeding up? And you can do this because looking out in space is looking back in time. If you see a galaxy 1,000,000 light years away, you're seeing the light took 1,000,000 years to get to you. You're seeing it as it was 1,000,000 years ago. So if you go out and find galaxies billions of light years away, you can see what the universe was doing 1,000,000,000 years ago or more, right? So we use the Keck telescope, use the Hubble Space Telescope to do this, and what they do is they look at supernovas. Okay? So they find these distant galaxies. That's a supernova there. It's an exploding star, and they're wonderful. They're all the same brightness. And by measuring them very carefully, you can see exactly how far away they are and how fast they're moving away from you. So you can actually measure the expansion rate as a function of time. There's another supernova there. There's another supernova. And these are some nearby supernova remnants. The blast wave from the exploded star looks like this after a few thousand years. But for the few weeks that a supernova happens, that one star becomes as bright as the 100 million or 100 billion stars in this galaxy. I don't know how big that galaxy is. That's why I had to say that. Okay, so what did they find? Well, they found, in fact, that in the past, the universe was expanding slower. That means today it's expanding faster. That means the expansion is speeding up, which means that vacuum energy is driving the expansion. Any kind of ordinary material would have slowed the universe down as it expanded, but it's speeding up. So we are actually going through this exponential expansion that I described. We're actually in it right now. Okay, this was a shock to the scientific world, even though it was a theoretical possibility for 50 years. People didn't expect it. But it was called the Science Story of the Year by Science Magazine in 1999. So it's an amazing discovery. And one nice thing about it is that you can say, okay, I said the Higgs field was more than 1 trillion tons per cc. These guys can measure how much is the vacuum energy. And they can do it. It's about 10 to the minus 29 grams per cc. That's about 1 proton mass per cubic foot. So this makes the cosmological constant problem even more acute. You have to take this trillions of tons, cancel it off, and leave 10 to the minus 29 grams in each cubic centimeter. This is a very precise cancellation, and nobody has a clue on what mechanism is causing that. Okay. So this stuff, even though it doesn't seem like much, 1 proton per cubic foot, there's a lot of space out there. And in fact, if you add up the stuff in the vacuum, it's 10 times more than all the atoms and everything known. Okay? It's twice as much as the mysterious dark matter. So this vacuum energy, that energy of empty space, we now know is the dominant substance in the universe. It's driving the universe. It's determining our fate. Okay? So there we are. Well, where are we going to go from here? Okay? How are we going to make progress? We don't understand this. Well, particle experimentalists can maybe find the Higgs and tell us if this is right or not. And there are other theoretical ideas such as supersymmetry that really help in this cancellation. Okay? Astronomers can measure the expansion rate more accurately and tell us a very important thing: is this vacuum energy changing with time or not? The cosmological constant is a constant with time. The vacuum energy could change. If they find it changing with time, it'll be a great clue on what kind of quantum field is responsible. We don't know what quantum field is responsible for the expansion of the universe now. But what we really need here is a theory. We need a theory that'll predict what's going on here in the vacuum and tell us that. If you think about what kind of theory could do this, it turns out there's really only one that people have thought of, and this is this brand new theory, not that new, but theoretically new, superstring theory. Okay? Superstring theory is the first consistent theory we have of quantum gravity. It's a very speculative theory at this point, but it holds a lot of promise. Now, you may know that Einstein wasted the last decades of his life trying to find a unified field theory. He wanted to make electromagnetism and gravity all part of one unified theory. And he failed miserably, and it's clear now why he failed miserably. He didn't know about the Standard Model. He didn't know about gauge symmetries. He didn't know about nuclear forces or quarks or any of the things you would need to put together a unified field theory. But his dream of a unified field theory stayed on, and finally, maybe 10 or 15 years ago, the superstring theory came along, and that is the first candidate we have had. It's a very beautiful and elegant theory, but unlike the theories I've talked about before, which are well tested by experiment, superstring theory has no experimental test. So it's speculative. Okay? So I'm shifting into a much more speculative place right now. Okay? Well, in string theory, there's only one elementary particle, and it's not a particle at all. It's a loop of string. Okay? And there's only one force in string theory, and that force is two strings can come together and join, and then they can split apart. That's it. Very nice, huh? Very simple. The beautiful thing is that different particles that we know of, like electrons and quarks and photons, basically these are just the same loops of string vibrating or winding in different ways. Okay? Now, one very elegant thing about the superstring theory is that it automatically includes supersymmetry, this neat symmetry that helps with these cancellations. Okay? But even more elegant and important is that it automatically includes loops of strings that vibrate like gravitons. In other words, it automatically includes particles, quantized particles that look like gravity. So it's automatically a quantum theory of gravity. Okay? So it's great. So it's a beautiful theory with lots of potential, but it has some serious obstacles. Okay? The first one is that these loops of strings are very, very small, 10 to the minus 33 centimeters. They're so small that you'll never see these strings in the biggest accelerator that you can even think of. Okay? You'd need an accelerator the size of the galaxy in order to measure these things. So we're never going to see these strings. This is very bad for physics, which likes some data to prove things, right? The second interesting thing about string theory, there's many, but a very interesting thing is that the strings are only consistent if you have 10 dimensions, 9 space and 1 time dimension. Okay? Now we know there's 3 dimensions. 1, space dimensions, 2, 3 right angles. In superstring theory, you have to have 6 other spatial dimensions to make the theory make sense. Okay, well this would seem like this would rule out the theory right now, right? Because where are they, right? But in fact, this may not be a bug, it may be a feature. Because these extra dimensions could exist and just be curled up so small that you can't see them. Okay? Let me give you an example. If you take a piece of paper, flat piece of paper, that's 2 dimensions, right? I could curl up one of the dimensions into a little tube, right? And if I curled it up so small and you were going along it, maybe you'd only think there was 1 dimension. You wouldn't see the little internal dimension. And in fact, I could take a piece of paper and I could curl it up like a ball, or I could curl it up like a donut with a hole in it, right? So these 6 extra dimensions are hypothesized to be curled up into something so small that you can't see them. Now, why this is a feature is it turns out that the way these internal dimensions, these extra dimensions curl up, determine what particles are in the universe. In fact, you can show that the number, like a donut has 1 hole in it, that the number of generations turns out to be the number of holes in the curled up dimensions. Okay? So if you go back to the standard model of particle physics, you notice that there were 3 generations. Well, that says that these curled up 6 extra dimensions have 3 holes in the internal Calabi-Yau manifold. Okay? Well, that's really cool. So what that means then is that now this is empty space I'm talking about curling up. So once again, we see it's empty space that's determining things. The content of empty space is determining the fate of the universe, and the topology, or the shape of empty space. We have here like 3 generations. Nobody knows why are there 3 copies. The muon and tau are just like the electron, except with a different mass. Why are they there? Well, superstring theory says, well, it's because the way empty space curls up determines the number of generations. Okay? It turns out many of the other properties are determined by how this thing curls up. Okay? So if this theory is correct, the shape of the universe determines the most important quantities of the universe and the content. For example, in another universe, these internal dimensions might curl up differently, and maybe you would have only 1 type of electron, or maybe you'd have 15 different types of electrons, right? Or you could have completely different particles in another universe by curling up empty space in a different way. Okay? How about another universe where instead of 6 dimensions curling up, leaving 3 big ones that we see, how about if 5 of them curled up, leaving you with a 4-dimensional universe? Or maybe more would, 2-dimensional. All these properties of the universe that we just take for granted turn out to depend in superstring theory on how these extra dimensions curl up. Okay? So this sounds like science fiction, but what is true is that the properties of the vacuum are turning out to determine many of the most important properties of the world, okay, around us. Now I should stop here, but I would like to finish by just asking whether all this bizarre stuff I've been talking about is actually important. Okay? Does anybody care? Does it matter if we know it or not? Is it ever going to be of any practical use? Okay? Well, the honest answer is I don't know. But it does remind me of a similar question asked to Michael Faraday by Prime Minister Gladstone of England a couple hundred years ago. Michael Faraday was the most famous scientist of his day. He discovered the laws of electricity and magnetism, and some of them, and how wires could move. His inventions, his discoveries led straight to electric motors, generators, and then pretty directly to radio and all of electronics. Okay. So Prime Minister Gladstone is touring the lab, he finishes touring the lab, and he sees the Leyden jars, and he sees the wires being moved. He says, "Oh, Professor Faraday, this is all very well and good, but can you tell me, is this electricity ever going to be good for anything?" And Faraday, was a curiosity-based researcher. He wasn't thinking about practical things. He says, "I don't know." So I'll stop there. I said there had to be this huge cancellation to have this of the Higgs to get to the little one. Well, you need the Higgs boson field to be exactly as it says in the standard model in order to slow your hand down. If you had that little tiny difference only, your hand would be going way too fast. And you couldn't get the masses of particles. Those masses are fixed by experimental quantities, such as the mass of the W boson and the Z boson and other properties. It's not a free parameter of the theory. We know that trillions of tons per cc is not an adjustable parameter at this point, because we've measured, it's measured. What can we say? Okay, he asked whether the presence of the Higgs field has a preferred frame of reference. As you know, Einstein says there is no preferred frame of reference, but in fact it's not a preferred frame of reference, it is the vacuum. It is Lorentz invariant. In other words, more technically, if you're moving along, you can't tell the difference. The vacuum is the same for every observer. So, yeah, it's empty space, really is. Yeah, I know that doesn't sound too satisfying, but hey. What turned on the Higgs field in the early universe? When the universe was very young, it was very hot. And what you can actually show is that when it was very hot and particles were interacting so fast that the potential that sets the Higgs boson field was actually turned off, was symmetric, okay? And so what happened was the universe got to a cool enough temperature that the field theory could start to operate and the vacuum, the nature of the vacuum changed. We actually have this a lot in early universe. We have the true vacuum and then we have the false vacuum. So we would say the nature of the vacuum changes as a function of temperature in the early universe. That's, again, a subtle concept, and you'd have to write down some math to show you what it really means. Yes?
Is there any theoretical upper bound on the mass of the Higgs boson?
Depends on what you want to go with. Typically, in normal particle physics, yes, it's around a TeV, or 1,000 times the mass of the proton. That's what people think. What happens if you make the Higgs boson more massive than that is the beautiful standard model perturbation theory starts to break down, and we can't explain why it works so well. Now, it could be that something else by coincidence makes it work so well. So people have argued that. But I think that around 1,000 GeV is where it should be, maybe 2,000, around that. And then we searched from 0 up to 100. So we still have the big window left to search, and that's exactly what the LHC in Geneva is going to try to do, and what Fermilab is trying to do. Could the Higgs field vary in the universe? I mean, this didn't used to be a question that anyone would even think about asking. But now that we have measured the vacuum energy, it's a worthwhile question to ask. And the Higgs field probably not. If the Higgs field did vary, then things like the electron mass would vary, okay? But I don't think it's really been thought about. The vacuum energy that we think, if it's a changing vacuum energy, then in fact it would vary in space as well as time. So these are brand new questions, and they're good ones. And this is where some of the theoretical work is going right now. Yes?
If you assume that the measurements at CERN have identified a Higgs boson,
yes,
what mass is inferred by those measurements?
It's around 100, a little more than 100 GeV. So right near the top of right at the limit of their measurability. But I didn't even talk about the properties, the quantum properties of the vacuum. He said, how does the Higgs field vacuum relate to the particle, the 0-point energy? You hear people talking about particles appearing and disappearing. And that also creates a vacuum energy. In fact, in point particle physics, that creates an infinite vacuum energy. people have figured out that you're allowed to subtract that. There's technical ways to subtract it. The quantum vacuum is even more complicated. Again, string theory seems to be the way to approach this. And again, it's part of the cosmological constant problem. Using the Higgs field shows you something you know exists. This could be there, it could not be. There may be something more complicated that cancels that out. Supersymmetry, for instance, cancels out that kind of quantum vacuum. So, I know that wasn't a very complete answer, or very pure, but that is another contribution to the vacuum energy that I didn't even discuss. And it's probably there. It probably has to. It must also be canceled out to this extreme accuracy as well. It's not infinite if string theory is right, because strings are a finite size, and so there's a smallest possible thing, and so a biggest possible energy you can have. Any reason that the anti-Higgs field that cancels it doesn't affect our masses, and in fact it's not an anti-Higgs field. It just has to be some other field with negative energy density. So it probably has nothing to do with the Higgs field. If supersymmetry is right, it may have something to do with some supersymmetric partner of the Higgs field, though it may not even in that case. We don't know what it is. It's just some other field. That's the level of knowledge. So how could you experimentally verify superstring theory? Well, you can't see the loops of string directly, but maybe if you had a good theory and you could calculate with it. The main problem is you can't calculate. If you could calculate that exactly what the masses of all the particles were, that would be fantastic. And that might be possible if you could measure the exact shapes of these internal dimensions. There has been some very interesting, they're not really confirmations, but they've managed to calculate black hole radiation in string theory and get the right answer in a way that was completely independent of any way they did it before. A very exciting result that led people to think string theory might be right. You could possibly calculate the number of space-time dimensions. You could calculate. You would like to be able to calculate from first principles this entire table. And if you did that, even without direct measurement of the strings, you'd start to believe it. Plus, if you could do that, you may be able to calculate some things that haven't been seen yet and then predict them. That would be the hope. Like maybe you could predict some other kinds of neutrinos, some other funny things. How the Big Bang happened, something like that.